We had 18 months to develop a car.
Hello everyone, welcome to my platform. Glad you are here. I am honored this week to be welcoming Mr. Joe Rothenberg. Mr. Rothenberg was a guiding force behind the first in-space servicing mission of the Hubble Space Telescope for NASA, and which in itself is a massive accomplishment. Mr. Rothenberg has an incredible career spanning over 6 decades and has served in almost every single technical and leadership role within NASA. He started his career in 1964, and 19 years later, in 1983, he entered Goddard as an operations manager for the Hubble Space Telescope. In 1987, he was appointed as chief of Goddard's Mission Operations Division, and in 1989, 2 years later after that, he was appointed as Deputy Director of Mission Operations and Data Systems. In 1990, he was appointed as the Associate Director for Flight Projects for Hubble. In 1995, he was appointed as Goddard's overall director, and 3 years later, he was appointed by NASA as the Associate Administrator for Spaceflight. For almost a decade, from 2003 until 2011, Mr. Rothenberg represented the Swedish Space Corporation as a President and Senior Vice President of International Development. He was Google's Engineering Director for Terra Bella, which was formerly known as Skybox and was acquired by Google for $500 million in 2014. Mr. Rothenberg was also the chairman of the Technical Advisory Board governing Skybox Images. Since 2016, he has chaired and taken part in multiple technical and executive advisory boards, including Conrad Foundation and 7Benefit Limited. Currently, Mr. Rothenberg is member of the board of directors at Conrad Space Development Corporation. Now, this interview is not short by any means. It is 5 hours long. I was extremely eager to understand every single detail of the career path of Mr. Rothenberg, every single challenge encountered, every single obstacle that had to be overcome. He was extremely humble and kind to be able to allocate 3 different recording sessions to my initiative, and I want to thank him for that. To make this easier for you to digest and for me to produce and edit, I will produce this as 3 different chapters, i.e. 3 different videos, each one covering a specific aspect of Mr. Rothenberg's life. Usually, at least I believe so, I try to withhold my enthusiasm for those interviews and make them look extremely professional. That is the premise of my channel. This is what I do. I couldn't help but smile throughout the entire process in the face of the sheer amount of knowledge I gained from my discussion with Mr. Rothenberg. You have to also understand that the totality basically of my guests, they are volunteers. They volunteer their valuable time to enlighten me and you guys without necessarily getting something back. These are good-hearted, first of all, but accomplished professionals and leaders who freely allocate their time to educate the young generation. I want to thank all of them for that. Now, it is a very rare occasion that I can completely unfold my thought process and ask every single question I want to ask to every individual. Usually I have about 30 to 40 minutes. It is very difficult to compress somebody's career in 30 to 40 minutes and extract lessons from it. It can be enough, but it is not always enough. This interview with Mr. Rothenberg stands as one of those rare occasions. Together with us, you will understand every single decision an awarded top leader at NASA made throughout his career. You will be immersed into the world of difficult decisions, losses, major project breakthroughs, people management skills, what went right, what went wrong, what would he do differently if he was to go back and do it all over again. This interview, in my opinion, can be considered a fairly complete roadmap, a point of reference if you want, without exaggerating, for every single individual who wants to become a leader. You don't necessarily have to belong or aspiring to enter the aerospace industry. Doesn't matter which industry you want to go. I don't believe this interview should be viewed only once. I believe you should be revisiting this interview, watching it again and again and again, At least when I was editing it, every single time I was viewing it with a different point of view, extracting a different lesson each time. I don't want to drag this any longer. I want to let Mr. Rothenberg speak his truth, and you can make a decision as far as the value of the interview. But I hope you find it in the same way I did. How is the decision going to be made for a program when it goes against the political line that the government has drawn in NASA? Have you ever encountered a program like this?
If the congressional language said they must buy a launch vehicle from SpaceX, it wouldn't be that prescriptive, but it will be prescriptive. It could be, okay, for a certain kind of mission where if you don't buy it from SpaceX or somebody else who has it one commercially, you're going to have to develop it, and they don't want, that obviously becomes prohibitive. How was the culture after 1986? So in the late 80s, after the accident happened with the Challenger in NASA?
Obviously, there was more formality to the decision process and more rules in place after the Challenger. For example, the fact that management overruled an engineer, that was the principal. That's what caused the problem. But the problem, I mean, was the design. But nevertheless, if they lived by the temperatures you pointed out, good chance they wouldn't have had that problem. But when I was asked to take over lead the repair mission, was in the end of July of 1990. At that point, it was a national disgrace, a national joke. The comedians, everybody. So that had a rippling effect. Okay, Congress, of course, wasn't going to stand up and support something that was an embarrassment to the government. And
in spades will be remembered as stepping up to the challenge and knocking it down and turning it around into a victory.
Thank you for being here. Thank you for doing this. I believe it's going to be extremely insightful to me and to the young people who want to enter the industry to listen from your experience, mainly the major challenges, problems that you solved throughout your career. As we said, you have over 60 years of experience in space systems, over two decades of experience within NASA in business government positions, a lot of commercial experience in the new space industry as well. So thank you for being here.
oh, my pleasure, my pleasure.
Right. If I may, I can take you back to 1964. So exactly 60 years when you entered Grumman. So that was your first role, right?
Yes, though I did 4 years in the Navy and got introduced to an entire system, a fire control system for releasing bombs. So I got a good exposure as a technician to computers, to both digital and analog computers, optical systems, radar, gyros, stabilization and control systems. It was, in hindsight, I got exposure to a system very early in my career. And that's what sort of stimulated me to say, how did someone put all this together? How did they even think? How did they, the system was to solve a problem, was to be able to drop a bomb precisely. How did someone figure that out? How did they even put it? How did they know how the pieces work together? I mean, went from I don't care. I just want to see the world and travel in the Navy to getting exposed to technology and a system. And then my curiosity immediately rose, and that's what generated the interest to buckle down and go to college when I got out of the Navy when it died. So I really, that was kind of the spark that lit the whole thing. Although in the very early in that, when I go back to my elementary school, I was very interested in science at that time. And for whatever reason, in junior high school and high school, I sort of lost interest in it and much more interested in having fun and not doing well in school. And then the Navy turned that around. But so my early days at Grumman, one, I was fortunate out of college. Number one, I only went to a 2-year community college to start with, because coming out of the Navy, that's all I could afford. I could live with my parents. My father really couldn't afford to put my brother and I through college simultaneously. He'd help in any way he could, but I mean, so I went to a community college and it was free. That was, I was a commuter and then I worked nights. So when I graduated, I theoretically was an educated technician. I did have experience, and I was fortunate enough to get hired by Grumman, not knowing what I was getting into. I had no idea what I was, being hired for exactly. It just sounded interesting, but the first day I didn't know come to work in work clothes for doing a technician work or wearing a suit or what. I did choose to wear a suit, and I figured I could always get it dirty and change if I had to. But so I got involved in instrumentation early in the game, and that was again a systems problem. You were putting together, you had to learn the system in order to determine the measurements and you had to make and how you were going to make them. And you learned the technology, various technologies, depending on whether you were worried about a thermal environment, a vibration environment, but humidity environment, humidity control, life support, all of these different and elements of any system. And in those days, there was Apollo being developed, or challenges that needed testing and development and that needed instrumentation to make the measurements to support the test. So I got exposed during that to a lot of different pieces of a system. Again, still not really knowing how it went together. It took me quite a bit of trial and error and learning from other people and mentoring, being mentored, before I really began to understand systems engineering and how a system is designed, architected, and how you make decisions of allocating capabilities or performance to different pieces of the system. And then finally, how you interface them, put them together, test them, build them, and launch them.
You brought up two very important points right there. The first thing is systems engineering. Me as a young engineer, systems thinking is something that I can say that we lack. We're not taught during our university time, during our bachelor degrees, how to be systems thinkers. We have practical applications, we have some practical tasks, but it's not until we enter the industry that we start developing this kind of systems thinking approach and how everything connects to each other, because we're kind of, I'd say, fragmented. We want to focus on our roles as engineers. We don't really want to see how what we are making applies into everything that we are doing as a whole business or as a whole system for that matter. And the second thing you said is mentors. Now, I've had discussions with loads of people, and I'm divided in two different, basically, fields. So the first one is the people who say, well, you don't need a mentor. What is a mentor going to do for you? They have the experience, they can maybe guide you, but at the end of the day, you have to pave your own way. The second field of people says that the mentor is the best thing you're going to have in your life. What is your take on mentors in general?
I have to answer the question with a little analogy. It depends on the mentor, okay? Some mentors are this is the way we always did it, and I'm going to help you do it that way. Other mentors are looking at you as bringing fresh thinking and an approach to doing something, whether it be designing something or solving a problem. But you're solving a problem. I think your characterization of engineers as problem solvers is a good one, at least for my personal career. So I think a mentor that looks and hears out what you're trying to do, how are you going to do it, and asks you questions to get you thinking of things you might not have thought of, instead of saying, no, here's how you do it, here's exactly the way you do it. And I've had both, okay? I've had those that are very prescriptive because they grew up and they're at a point in their career where they've done a lot, done everything in many cases, and they know what worked. Forward thinking mentors that are maybe mid-career or even just a few years ahead of you, and I had one that was just a few years ahead of me, are realize that technology is emerging, and from the time I started till to today, the rise in technology and innovation and compute power, compute to begin with, and compute power and access to tools, engineering tools, has grown dramatically. I mean, I would argue in the 50s, 40s, and 50s, even into the 60s, most designs were replicating or systems were architected around the way military systems were for aircraft and ships for the Second World War. It was a power system. Everything was compartmentalized. Systems operated. There was an interface between them. That interface was defined, but they were isolated. And today's systems are highly integrated to start with. There might be a central computer that's operating and doing, being the orchestrator for all subsystems, managing power, managing thermal, looking on a satellite, looking across power and thermal, looking across data systems, looking at communications links and optimizing downlinks based on the amount of power where they are in an orbit over a ground station. So that kind of thinking wasn't possible, and certainly not in the culture of the engineers in the again developed weapon systems for the Second World War, the Korean War, into the 60s. When I got involved in spacecraft, even to the point of how the company was organized that replicated the past and didn't look at where it wanted to go in the future. And that's an important thing. So again, a mentor who is not trying to replicate the past, but has some idea that I might come to the party with a different viewpoint and a different set of education, a different set of tools, and allow me to exercise my thinking and my plan, and then looking and guiding me in the form of, have you thought about that? Have you thought about, that's the kind of mentoring that I think is very, very important. The kind that there's other things about mentoring also, and it's the personal, the interaction with people, how you dress, how you interact with people. A mentor will give you some guidance in that, and little things when you start out early in your career out of school and know nothing. That was me, all of those things. I did a lot by watching. I always kid, but the first day to work, I didn't know whether I was wear a suit or tie. Second thing, my immediate boss was out. I think for most of the first week, he was on travel. And so his boss gave me a bunch of pile of paper to read and told me, go sit over there and read. He didn't introduce me to anybody else in the team or anything. He just gave me, he was very friendly. When it came lunchtime, everybody got up and went. I didn't know where to go. and it was a very complex building, and so I didn't know how I was going to get back, so I followed somebody. Again, I was a little reticent to say, hey, I'm new, where are we going? I just followed them, and I followed them to lunch, and I watched when they got up, I followed them back. Fortunately, we're going back, but seriously, it was those kind of things early in the game, getting involved in a technical society in my field, and learning, a little bit broader knowledge about my field, and even in areas that I'm not working today, but off in the future I might be working. That mentoring was given to me by, I ought to join the Instrument Society in Long Island. I ought to go to meetings, I ought to listen, it didn't cost anything, or the cost was not the issue. But that kind of mentoring, if somebody hadn't suggested that, I wouldn't have even thought about it. So there's many levels to mentoring, is what I'm trying to say, and I think they're useful. I also think that I'll use the word management, but as you get along the way and become a first line supervisor, mentoring is important there. How to deal with you need somebody to talk to. You're going to face personnel challenges that you have no experience base in, unless you somehow experienced them before. But you're going to face personnel challenges. You do need somebody to talk to. Taking a little course in basic supervision, learning about them, Maslow's hierarchy of needs, things that tell you how people might be thinking that is different from how you think, is important to be aware of. And you get that through mentoring, through informal education, and well, you don't always get that in college courses, even in college business courses. You get that much more in job-related courses. So, and it's another form of mentoring in my mind, but
you're giving it a very different dimension, I think. I also think that my generation lacks patience. So when we go up to a mentor, all we want is to quote unquote use their advice to elevate ourselves through our careers. How can I get this position? How can I get into this corporation? How can I do this? How can I become a manager faster than everybody else? You gave a different dimension. You said the person who will help you to even dress. So a mentor for life, not just a corporate mentor that you see every day in the office and then you don't see them for the rest of the day or the week. A very different perspective, I think.
yes, I would agree. I see that in my own grandchildren who are now in their 20s, and that's exactly. I mean, one of them just got promoted, just got a nice raise along with the promotion, and she's maybe a month after this happened. I said, "Congratulations." And she says, "How do I go about asking for more money?" I said, "You just got a promotion. You just got and I try to tell them that, my personal experience has been, and I had that problem when I was a division chief, and that was probably in the mid '80s, so like the first third of my career, sort of about 20 years working, 20. We got a new secretary, and the first question she asked me is, how do I get to be a GS7 or a GS9? I don't remember what it was. That was the first question she had. She just got promoted into this job. And there's nothing wrong with saying, hey, here's what you have to do. But she had the mentality of people today, like, will it be 3 months or 5 months? Instead of that. And my advice has always been, even today, is do the best job you can, what you're doing. Get yourself recognized, go the extra mile, make people know that you care. And the problem will then be to select the right opportunity, because you'll get in today's environment, you'll get opportunities, and it may be changing companies, it may be leaving the government if you're government employed, and your problem will be to make the right decision at that time, and so, but they don't see that. They don't believe that something might happen 3 months or 6 months or 9 months downstream. They gotta, how do I make that happen? And, my advice goes back to do the best job you can. Now, let me take one other thing though. there's different kinds of mentoring, as you point out, and one is how do I get a promotion? How do I advance my career? Others are how do I accomplish this project I want to take on, and here's what I'm doing, and what do you think? And any guidance, and a good mentor again will look at it and not try to tell them how to do it, but try to make sure they're addressing all of the challenges. I gave that little anecdote for a reason. Not too long ago, 2011, when I joined or became a consultant and essentially joined a full-time consultant for Skybox. Skybox was comprised of a bunch of young people. The engineering staff was pretty much in their early to mid 20s. There were a couple, one turned 30 when I was in. They had one or two people had a little bit of space experience. They brought in a CEO who I happen to work with many times over, who asked me to come in and talk to them, and I discovered and see what they might need. And just a period, that was the only thing. Can I stop in? I was out in California on another thing. He heard of it. I was out there. He said, "Hey, you mind coming up to Mountain View and I want you to talk to our engineering team." And what I found out is they had a critical design review or preliminary, I guess it was a CDR. I don't remember, either a preliminary or a critical design review. But they had a design review, and they brought in a traditional review team that typically government projects had. Now, this wasn't a government project. It was a commercial build of a satellite, all with private money, private investment. Their customer were themselves. They were building this Skybox constellation, which if you've done any reading, you might know what it is, which was meant to be able to put up a high performance microsat that would perform as well as a $200 million ICONOS Earth remote sensing satellite, same resolution, image quality, but build it for a recurring cost of $5 million a copy, instrument and all. They did it. However, when they were there, when they started out with a clean sheet of paper. They didn't know what couldn't be done. They went and used commercial parts and tested them and demonstrated they could survive the environment versus buying already radiation hardened mill space or government space level qualified parts. The microprocessor they needed 7 of them. They spent $2,000 on each one. Looked at its susceptibility to radiation, put in a redundant processing as well as testing of the software when they got a radiation hit to be able to react and do something, as well as some selective shielding. And they spent another $500 or so on each of to do that initial design. But for $2,000 and amortized over the 7 of them and the times 21 spacecraft, they replaced what would have been a $200,000 per processor, which would have been $1.4 million per spacecraft just in microprocessors, because they looked at it and said, "Why do I need that? This will do the job." They did the same with detector technology. Now, going back to why I brought up this in the first place. So the critical design review team was old school, and they come in and all they wanted to know, they generated what requests for information or action items, call it what you want. They generated 500 of them, of which there were about 20 that had any substance. The other 480 was, why don't you do it this way? This is the way we always did it. It was some variation of that. And so these guys were pretty discouraged. They had enough self-confidence, even though they didn't have the experience, to say, "Nope, we're going to do it the way we're doing it because we can't afford that." So when I got there, they looked at me as another elephant. I'm going to come in and step in a cabbage patch. And I started talking to them for about 15 or 20 minutes, and it just dawned on me. I saw what happened to them. They told me about these RIDs, and they told me they thought maybe a couple of them were, 5 or 10 of them or 20 of them were useful, but the rest were make work, and they just threw them aside. So I listened to them for a little while. I said, you know what, you guys, you sound like, you're on the right track. All the things I hear you doing sound like all the right things, but you don't know what you don't know, and you don't know what perils are in front of you in terms of. And so I said, instead of getting an outside review team, how about I establish this thing? I dreamed it up in real time, a technical advisory group. And there'll be a bunch of mentors. I will hand select them, and I assure you will get a say. You'll get to interview them and make sure that you're comfortable, you can work with them. But I promise you that every one of them will have hands-on current experience, but maybe have 30, 40, 50 years, but they've hands-on. They're not the typical buyer who, government, engineer who buys a contractor to do something, writes a spec, but these guys are actually doing the work. Okay, so I put together a team, trolled them by them, and went through a set of interviews. Then I set up a mechanism by which they could call these guys up anytime they want and ask them a question. I made them a library in effect, and we had reviews. We went now had another CDR, real CDR, but instead of having it in the conventional way, we told them, we're not looking for piles of viewgraphs. We're looking for you to tell your story, what you're doing, how you're gonna, how you convince yourself the system will work, what analysis tools you're using, and what test program you put in place. So the first review we had with these guys, I also set the mentors around the table, and every time there was something that my guys did not, the technical advisory group didn't understand, instead of writing a RID down and giving it to somebody, they raised the question in real time, and we had enough people in the room that we had to come to agreement that it was a real problem and not just a worry that this guy had. In many cases, they could answer the question after in real time and didn't need paper to do it. So what we ended up doing, and then if there was a problem, we took an action item. And somebody took the lead on that action item. And so at the end, we ended up like 20 to 25 real problems that needed to be addressed. And somebody owned each one. Turns out that in addition to mentoring, in addition to reviewing, in some cases, the expertise to address that problem was in the tag and so we signed up to take the lead and help them solve the problem. So we became a constructive review group and process, and that went from one review into they couldn't get enough of these guys. The young engineers, they would feel free, and we set it up, and the tag, most of them had day jobs. Most of them were, a couple of them owned their own companies, and they were in good shape, retirees, and they really weren't that interested in making money. That wasn't why they were there. So we gave them a budget, a monthly budget. Half of them didn't use it, didn't even charge for it. We found one guy and said, I've been working 60, 70 hours a month, and you only gave me a 20. And he did this after a year. He said, I averaged probably about 60 hours a month. He said, but I've only billed for 20. I said, that was only a working number. And we didn't go back and pay him, but that's how the thinking was. They were enjoying work. And the other thing is the review team, and I'll let you turn us back to you. The review team, when they came, again, I talked about reflecting the past. And when the review team came in, they looked at what these guys were doing, and they used a different design approach for the satellite than normally any satellite had been developed. They used one that was prevalent in the automotive industry. Was a bus with processes around, and everything talked to each other through this bus. It was called a CAN bus design. And the review team said, we wouldn't have done it that way. If we had a clean sheet, we wouldn't have done it that way. Not because it isn't the best way, it's because we wouldn't have thought of it. That was their feedback. They wouldn't have thought of approaching it that way. These guys, they didn't, they didn't know what couldn't be done. They took what they thought would work for the design they needed and the performance they needed, and went ahead and developed it. And it turned out it used a whole different approach, a whole different design approach. It turned out it was 100% redundant, fully reliable, and it was a $5 million satellite with the performance of a $200 million satellite. And that was because they didn't know, they didn't look at the past and try to replicate it. They looked at the problem they were trying to solve, and they knew they had one constraint on it. That's another very important thing, is you need to have a cost constraint, and they had a cost constraint, and they made all the decisions based on, will it meet the performance and will it fit in the cost? And then I'll make it meet the environmental side of it. I'll do what I can to isolate it, protect it, and make it work in space. But can I find a piece of electronics that will solve the problem, a sensor, even if it's not space qualified, it meets my cost bogey, and then after that, I'll figure out how to qualify it. And they did that. And by the way, they tested it to the full environmental spec that NASA would test any satellite, and demonstrated and qualified it to that, and they pulled it off. But it was because they didn't try to replicate the past, and their mentors didn't try to make them do things like the past. And the mentors, I can say along the way, the tag may have covered 3 or 4 significant things that, had they not caught it, might, and not would, but might have caused a problem on orbit. And that was it. I mean, the rest, these guys, really, their thinking, their approach and everything was very sound. And again, there's a way that mentoring was important. They might have gotten there without mentoring. I think mentoring gave them confidence, because when the mentors came in, instead of and looked at what they were doing and really encouraged them versus jumping, trying to change what they were doing, gave them confidence that they understood what they were doing. I mean, these guys were really basic when it came to designing a light baffle. Went to a textbook and added a textbook, designed the light baffle. That's how they did things. They had no experience. And so and I look at them today, and a couple of them have their own companies. One of the guys, one of the systems engineers, guy who was the systems engineer, he had at that time about 5 years experience, a little bit with SpaceX. And I would say he's one of the finest systems engineers I ever got to work with. He now is CEO of his own company and making his own mark. But anyway, so I think mentoring, the way people think today are not, these guys weren't thinking at all about how they got ahead. In the commercial world, they were thinking about, how do I get this product out there? And once I do it, that was their job satisfaction. And by the way, I can also remember when Google bought them, and these same people sitting around the table at a meeting, and I'm sitting there and looking at them and saying, every one of these young guys who are now maybe 25 to 30 are millionaires already, and multi-millionaires already, because they developed something, Google bought it, they were stockholders, and so they got there, and that wasn't what they were looking for. They were really, really full of energy. And then I watched them, get engaged, get married, have children. I still keep in touch with many of them, and they're all doing well.
I can say what you said in 2011. That was skybox imaging, right?
Yes.
I believe from the way you describe it that it is management done right. These are principles. I mean, these are principles that nowadays are industry standard. But then you were paving the way, and what they tried to do with commercializing the satellite concept, taking a 200 million application down to 5 and commercializing it. That is something NASA tried to do as well with the spaceflight program. They were trying basically to create a freight train to space in the 1980s. Was this something that you drew from NASA working with them through the 80s and 90s? This approach of creating something from a clean sheet piece of paper and then consulting your team accordingly. Did they teach you that?
Yeah, yes, I can. When I mean, I was involved in the early, Grumman was one of the competitors bidding on Space Shuttle. And I was at that time working on the orbiting astronomical observatory, and program was coming to an end. And so I got involved a little bit on the proposal for the shuttle, a little bit on the study, and later on, Grumman did some work, even though they lost it, and I did some work on the space shuttle with Grumman. So I have some knowledge, and then later on it came under me when I was on NASA headquarters and got into 4 years. I got in quite deep, but so going back when they proposed the space shuttle, and I gotta I may have either number is far. They talked about $5 million launch, then it was $12 million at launch. And you look at those numbers, and that would have been a very competitive launch vehicle, okay? But what happened in the end is the launch cost went up to 75 to $150 million a launch with the expendables and fuel by the time they got it going. And that was the cost in the early 90s. So, decremented by 50% or 60% to the mid 80s, but it was still much far more expensive. It wasn't as competitive with launch vehicles as the Delta was out there, the Pegasus was out there. There were launch vehicles out there that were putting up payloads for far less money than it would cost them to integrate it. The shuttle became also human spaceflight, governed by NASA's human spaceflight culture, very conservative, very expensive. You had to adapt, commercial satellites had to adapt to the NASA rules and culture versus, and the same for the tracking data and relay satellite. Although it couldn't be used commercially because of the radio frequencies were government protected by the Department of Defense and NASA. They never wanted to open that up to commercial use because once they opened the door a little bit, commercial guys would take over their frequencies, but not back up. But the TDRS is the same way. They were designing an infrastructure and to be robust, and the user was kind of almost an afterthought rather than making it easier for the user. So it was a very expensive and time-consuming process to get a payload on board the space shuttle. Although they did, as you know, there's a number of communication satellites, international. However, the second point was Challenger came along, and Challenger really got to question, when we go up in space with humans, with human life at risk, it ought to be for a purpose that there's no other way we can do that job. We need humans, and we need the space shuttle to do it. We need humans up there. That became the criteria rather than let's see all the things we can do. It was anytime we went up there, there had to be a mission that required humans. That two things happened. Number one, the cost started going up, and more importantly, once the Challenger happened, the agency and Congress pushed back and said, "Hey, there really needs to be a rationale for having humans, carry a payload up." It could be something as simple as it's a very tricky payload and has the ability for humans to compensate for deploying, and stuff like that. It didn't have to be total human interaction, but they came very selective. The second thing is they really frowned upon commercial payloads after that too, because there were ways to get them up. The argument wasn't, and they weren't that cost competitive, so the commercial guys didn't. The guys that complained, the customers that complained were the people that did all the work, paid all the money to qualify their vehicle to fly on the shuttle, because you had, for example, one of the requirements that drove the design of a satellite was you had to have the ability to withstand the landing load. Should the shuttle have to abort and come around, there's a tremendous load on it, much higher, 7.5 Gs if I remember it, 12 Gs, some large number. It may have been 12 or 13 Gs that the satellite had to withstand without coming apart in the payload bay and, doing some damage or whatever. So that those are the people had some complaint, because they had a heavier satellite, because they had it built it stronger, and now they couldn't fly anymore. But the reason, and finally the shuttle, if you look back at it, had even at shutdown, even when they terminated, still had about 80 and 90 single point failures in the system. The technology was aging, but those single point failures was always there. It's what, when they designed it in the 70s, and built it in the air, things changed. I mean, technology changed. Things you could build far more reliable, and so it had this risk, high risk level of risk, even before Columbia, and Columbia just cemented it. That was it. It lost support for continuation.
I believe a lot of lessons came out of this. I remember an engineer from Morton Vehicle, his name was Alan McDonald. He was the person who went in front of the committee, and he said, well, we said clearly to not launch below 50 degrees Fahrenheit. And the Chairman Rogers told him, this is going to be in litigation for years to come. So it brought out, I think, an ocean of ethics in engineering. How was the culture back then? You joined NASA in 1983. How was the culture later, towards the end of the 90s, the 80s?
Say that again. I'm sorry. I
Yeah.
didn't. The question. I apologize.
Yeah. No worries. So how was the culture after 1986? So in the late 80s, after the accident happened with the Challenger in NASA?
How was what? I'm missing that word.
Yeah. The culture.
The conscience?
The culture in NASA,
Culture.
KUL.
Culture.
Yeah.
Well, obviously there was more formality to the decision process and more rules in place after the Challenger. For example, the fact that management overruled an engineer, and that was the principal. Not that's what caused the problem, but the problem, I mean, was the design. But nevertheless, if they lived by the temperatures you pointed out, good chance they wouldn't have had that problem. But having said that, they became more rigorous over time. However, what happens is over time. I mean, 90s, we safety was in everything we said. Okay, it was always safety, fly safe, and the administrator, was a very strong proponent of it. However, in practice, what I saw happen, and I would say, I don't want to say it caused Columbia, but certainly Columbia there were signs that I think the problem there is that there was an engineering culture, an operational engineering culture, rather than a design engineering culture running the program, and an operational culture doesn't tend to go back and look at the design they're given and question the design when they see problems. And they also didn't immediately conclude that a piece of foam and look at it and say, what F equals MA, what kind of acceleration could I get on this foam, and therefore what could be the effective mass of it as it hits the shuttle. They looked at it as innocuous. Okay. And the original design team at that time pretty much dissipated, and they were not really listened to because generally the design team wanted to, every time there was an anomaly, wanted to go back, halt everything, let's go look at it. The operational people wanted to keep it flying, and they would look to work around. So, having said that, an example, there was always on almost every launch a problem that cropped up that could have, had things gone the wrong way, could have affected the mission negatively. Give you a couple of examples, okay?
Mhm.
Two missions in particular. One of them was the John Glenn mission. One of the reasons John Glenn didn't fly earlier is people were always worried about killing a national hero in an accident. That was one of the undertones, and you know, they didn't, you know, they hesitated, although he wanted to fly. Finally, he earned it, and he got to fly again on his launch, okay? First thing that happened is the way a shuttle engine works, okay? Main engine works is the propellant comes down and goes through a series of tubes that are wrapped around the nozzle, okay? And that purpose of that is to cool down the nozzle, okay? So the propellant flows, cools it down, goes up into the pump, goes into a chamber. There's, you know, the locks and the hydrant, goes into a chamber. The chamber at the end of it has a plate, and the plate is a diffuser plate that takes the liquid, comes in and lets it come out as a kind of a spray. Okay, and there are about 400 holes in that thing. And because of the difference in temperature, one side you got, you know, fluid, the other side you got cryogenics, one side you got heat. You develop cracks between the holes, and the rules were, and based on analysis, that you could have up to, I believe it was 10 cracks. 10 holes with cracks, but you couldn't use those holes. So they developed a pin that you plugged the hole. So they inspected the plates between launches. They looked where there were cracks, if there was less than 10 cracked, and there was something about geometry too, if there were two adjacent ones. But they put a pin in. They used you know what a fish scale is, you know, just a scale. They used that to test and make sure it was a friction hole, and they used it to make sure that it held. Well, safety culture. So here we got a risk already. The risk is that we're flying with cracks in the thing, in the diffuser plate. We mitigated the risk by putting in a pin, and we mitigated that risk of that pin being in, you know, at the wrong end of the tolerance. You know, everything's got tolerances, the hole being at one, the large end, and the pin being at the small. We mitigated that by testing. Well, we flew the injector plate down 10 times with the pins in it. We recognized that, hey, we've never had a failure. So they stopped doing the pull test. You know, so what
That's
the
incredible.
culture here is new normal. You know, you're familiar with the concept of new normal. There's a new normal. Yeah, so they have these two risks they built in, and they accept those as no longer risks. They're just new normal. What happened on John Glenn motors? The pin came out. Not only did the pin come out, it cut some of those flow tubes. Those flow tubes I mentioned that in the nozzle, you know, the cooling tubes. It cut, I want to say 6 or 7. It turns out if you cut 9 or 10, that engine needs to be shut down. Okay, you lose enough fuel that you're not. So we cut 6 or 7.
So they
People
would
don't
have
know.
almost asymmetric thrust basically on the rockets.
No, that isn't the problem. The problem is that, yeah, you don't have enough contribution from that one engine.
Yeah.
You need all 3 engines and a certain predicted thrust to get you in orbit. You're not going to get it. You're going to lose altitude. So what happened on John Glenn? They didn't get to the orbit they intended. Nobody knew that because it wasn't that far off, and the mission went on as normal. But the fact that they think about it, that thing just had to rattle around a few more times and potentially. So that's the first thing that happened. Now, the second thing that happened is the drag chute the door on the drag chute came off on liftoff. And why it came off, every time there's this free hydrogen that goes off and ignites, and it, has many explosions all around as you're going up. Well, this explosion happened to happen right in front of the door. Okay, and the door's got some weak spots with the fasteners, and so it blew the door off. Now, it turned out nothing negative. The chute didn't come out, and everything was fine. But they went back, that particular one, they never analyzed that case in the analysis when they designed it. What happens if they get a free high? Third problem, and this is, remember, this was, 95, so they had, somewhere around 90, 90, the number wasn't always sequential, but 90 flights a day. The third problem, the hold down bolts, they got the solid rocket has these 4 hold down bolts around each of the rockets. I have one downstairs. But the point
Not
is,
an actual rocket, I assume.
yeah, I actually have one from a mission. What they do
Really?
was, after the mission, they take the hold down boat and they go hold down boat, and they clean them up and they put them on a plaque and give one to each crew member. And then when I
I
retired,
didn't know that.
yeah, they gave me one.
That's
So
incredible.
the
That's
hold down
incredible.
boats are frangible bolts. I could bring it up and show it if you want, but the hold down boats are frangible bolts that you blow 2 pyrotechnics, it blows them apart. Well, what was happening is they all weren't blowing. For whatever reason, some of them didn't ignite. So the solid ripped them out. Now, conceivable, that if 4 on one engine hole, they could get an uneven, or something. Nothing like that happened, but the fact that they just discovered on the John Glenn launch, and historically, that this had been happening. Again, launch 95. So there were these risks built in. Okay, the second, so that all of those happened on that one. I could give you a number. The other one, I was an instrumentation engineer. I told you the one piece of advice my boss gave me in a mentoring form that I remembered is, you never make a measurement an even number of times. Because if you get 2 readings and they're different, you don't know which one to believe. So you need to make it either once or 3 times or 5 times. In other words, you never, if you're using sensors to detect something and take action, you don't want to depend on 2 sensors, because if one of them, you can't distinguish whether it's a failed sensor or the environment is happening. So, having said that, the first launch that I got involved in when I took over spaceflight, on the uphill, well, the way you launch the way the shuttle performs, the way any rocket performs, is you throttle back the thrust as you get to maximum dynamic pressure.
So max Q, you throttle
Yeah,
back.
you throttle down the thrust a little bit, and then you pick it back up when you get
Yeah,
through
yeah.
that. Okay, so in this particular case, they were in the throttle down, or in the bucket they called it, and they had a detection of an over temperature. Okay, they had 2 sensors, and one was measuring pressure, and the other was measuring temperature, and one of them failed. I can't tell you whether the pressure one was failed, but these 2 sensors were the decision points for shutting down that engine. Because what they always worried about was, if you allowed, if you had a blade, a turbine blade come off, imbalanced engine, and it could take the shuttle out. It could just, come apart and take the other 2 engines out. So whenever there was any problem with pressure or temperature being not what they expected, they would shut the engine down. They would actually shut it down, and they depend on these 2 sensors. And the thing was in the bucket, and they made a decision in real time that it was a bad sensor, but they didn't know that. But they looked at enough other parameters in real time. The system could have acted and shut that thing down. They just were watching it close enough. So my only point here is that they had a system where they had an even number of measurements and they were getting the flight computer to make a decision based on two measurements, not being able to tell whether the sensor was bad or really had a problem. And then when I questioned that, I said, you know, I went to the first thing. So I made them go back and look at all of the measurements where they took an action that would either terminate or do something that would risk the shuttle flight, and make sure that there were no other cases where they were depending on an even number of measurements. And if they had an even number of measures, there needed to be a correlation from a third source. It could be another thing, okay, another phenomenon, okay. And they went back and looked, they only found one or two others, but then nevertheless, the thinking there is what bothered me. You know, somebody had thought way back on this decision process that somehow they were going to be able to tell it was a sensor or a real environment or a real environmental problem, and not do the wrong thing. And that was luck that they didn't do that and shut down that engine. So the shuttle had lots of things in it. The foam was coming off during my watch.
It was a very well-known problem. Yes. Yeah.
Yeah, they changed
I
the
remember
foam.
that.
Yeah, they changed the foam, you know, because of the environmental pollution of the materials in the original foam. They changed the design and they never really fully solved the problem. They reduced it. I mean, originally, when I first got there, they found there were popcorning. The shuttle had bubbles in it, and bubbles in the foam, and it was blowing off. They did solve that by eventually using something like golf spikes and, you know, taking all the holes out. And little by little, and we used to check every shuttle, used to be there when every shuttle landed. And one of the things we did, walk around and look at the damage to the abrasive material and the tiles, and watch it, you know, slowly but surely it was reducing. This one came off right at the connection. Yeah, and so anyway, the one that caused Columbia. But the point was that that risk was always there, and nobody did enough deep analysis to say what's all the things that could happen. You know, if a piece of foam came off, it didn't have to be very big to have enough mass at the right speed to, you know, had the engineering team been in place, they would have started running tests, did analysis, brought the thing to a switching hole. One final thing, we did that quietly after Eileen Collins's launch. We didn't announce we're grounding the shuttle, but we had a short on the uphill ride. Again, took out the redundant hydraulics. Had she had to switch over to redundant hydraulics, we would have had another disaster. But fortunately, the primary system worked. But the point was, we discovered that starting to get cracks in the Teflon wiring. It was, you know, 20 years old at that point, aging, and 20 or more years old, 30 years old. And so then we throttled back. We brought in Air Force people who had a lot of experience with Teflon wiring, and determined what tests we could do. But, you know, it's tough to test a wiring bundle when there's, you know, you can imagine the wiring bundles on the shuttle are enormous, and to look through it. And we were able to, we did some audits, is the best way to describe it, based on the recommendation of the review team. But it wasn't something we made a lot of noise about. Didn't want to get everybody thinking we're standing down on the shuttle. But there's a period, I think, for about 6 months we didn't launch, and I think that was probably 1999, 2000, probably right after Chandra was launched. If I think, no, I thought I had the Chandra.
No worries. No worries.
Anyway, I can't even yet. But anyway, so I don't know. Back to there were a lot of things with the shuttle that didn't lend itself to commercialization. I mean, the USA wanted to take it over, and I was for that. On the other hand, I didn't believe it was sustainable because the annual overhead bill. Number one, little difference between some of today's zones in the shuttle is Except for very unique parts, many of the parts used on SpaceX and even other commercial launch vehicles are not solely made for the use of SpaceX. They're made for other applications, and SpaceX has taken advantage of it. Most of the material parts, processes were developed for the shuttle. Uniquely, the vendors were tied to the shuttle, their livelihood, or they had a commitment principally to the shuttle. So we had to keep that marching army, as we called it, but the infrastructure working no matter what. Okay. We had to keep them in place, if we didn't have any launches, we still had to keep them. That was running about $3.2 billion a year in the 99, 2000 timeframe, whether we launched one launch or not. The cost of a launch, as I mentioned earlier, was anywhere from, at that point, 100 to 150 million, depending on whether it was EVAs, the expendables, how much training, etc. And so the most launches we were going to do were 6 or 8 a year, I think. At that point, we maybe could have done a dozen, but I don't think so. Turning them around and getting them ready, the number of people we had on the ground.
NASA wanted one every week, right? If I remember correctly.
Oh, yeah. Originally, it was going to be one every week for $5 million.
One every week.
Yep, yeah, they they lost that quickly. I mean, yeah, James Webb was going to cost $500 million. Hubble was going to cost $700 million or 300 maybe. In fact, I think it was close to 300, etc. Number one, development is tough. Number two, there are things beyond anybody's control, like change, and people don't realize how they riffle down into the costs. The long-term cost, but clearly, launching, the development costs on the show. The other thing is the government, unlike the commercial world, the government writes off the development costs. And I talk about the recurring costs. In the commercial world, you really have to factor in how do I recover the investment? Because you got to recover the investment at some point. So it's got to be, you can't just develop a satellite for $5 million and say the 70 million I put into developing the satellite. In that case, it wasn't quite that high, but the money has to be paid back at some point. The investors are looking for it. In the case of Skybox, it was paid back through a sale of the company. The intellectual property became very valuable in that case in the processes.
I assume you had the same experience with the Hubble Space Telescope and the resurfacing of it.
No, actually, you mean in terms of the cost?
In terms of the cost, exactly.
Actually, no. Turns out that when I was brought back to the Hubble program to head the repair mission, they had a budget. Senator Mikulski added $25 million to the budget, but the budget was $250 million a year. And it did several things. It did multiple things. It developed the next generation of instruments. Servicing was always planned. Refurbishment of spares and making sure we got spare engineering units of gyros and things like that. The science program, the Space Telescope Science Institute, and all of the grant money, all of the money went out to the research scientists using the telescope. So that 250 covered a lot of things, and it covered developing of the servicing capability. And so the commitment I made to the number one headquarters told me, no more money, period. That's it. You got a huge budget. And it was right. It was figure out how to use it, do whatever you have to do to move money around it. They let me, and what I did in the science community, they were very worried about me taking money from the next generation instruments to fix up. And so I made a pact with them that number one, I wouldn't touch the next generation instrument money. If I had to, they would have to approve it. And I invited them to every budget meeting I had. They had a participant, somebody who came to every budget meeting. There was total transparency. They gave up on that they found it very boring after about 4 months. But nevertheless, we forecasted the budget and the schedule. And literally, we absorbed CoStar, which was $50 million of and all the gyro, or we didn't ask for more money for any of that. And we, from the time we started the servicing mission, number one, we launched within 1 day of what we predicted when we laid out the program, the first servicing mission. And we never, within the budget, we maintained the next generation instruments. We did not run the money up. And the reason is we weren't doing a lot of new technology development. We weren't doing a lot of, we were doing, it was an engineering job, is the best way to look at it. It was an
Hubble
engineering.
started as a clean sheet, sorry for interrupting. Hubble started as a clean sheet in 1946, if I remember correctly.
Well, in 1946 or 47, Lyman Spitzer, along with, I forget, a couple of, they came up with the notion of being able to, being able to, at that point, have a telescope that was above the Earth's atmosphere. Then I forget the name of the guy now. He was the project manager for a while, way back in the 60s, late 50s, 60s of Hubble. Initial first, he was in not Hubble, but of OAO. He developed the concept of the three-axis stabilization, and so yeah, the idea started. The 50s developed the concept of three-axis stabilization, and then OAO, the first series of optical satellites that got up to a 38-inch mirror on the Princeton experiment, if I remember correctly, although 4 of them, that went on in the 60s, and in about 67 or 68, we started talking about the Large Space Telescope. There was a family. We went from 1 meter to 1.5 meters. There was the belief that there was going to be this infinite amount of money being, and they finally came up, and the second thing we started doing in the mid-60s, Seppelina, and I was at Grumman at the time, and I was not his counterpart, I was supporting him, let me put it that way, as a contractor, was developing concepts for servicing satellites on orbit. But it wasn't how to service them, it was how to design for serviceability. Do I have connectors that mate modules? These connectors need to have a lot of flexibility in how they mated, such that they could be self-aligning when they mated. Bolts that were captured when you pulled them out. Thermal surfaces that didn't depend on applying thermal grease when you changed out component. There were a lot of ideas on how to service a satellite that really went into the design. Without that, and so when Hubble, there was a study done in late 60s called the summer study, and that determined, came out the other end that said the way uptime versus reliability was kind of how they optimized. How do we maximize uptime? That is collecting photons on orbit. And how much do we invest in reliability to maximize that uptime? And that's when they came up with the way to maximize that was to be able to service it on orbit and return it to Earth every 5 years for refurbishment. Well, along the way, they realized the folly of returning it to Earth. I mean, number one, it would be a big vacuum cleaner sucking in all the contamination. Number two, once you got on the ground, getting back off the ground was just as difficult as starting a new program, right? Because it would have been tough, and so they dropped that idea and planned the servicing mission every 3 years, and had a budget laid out for it to sustain it. So servicing mission used the first servicing mission used the existing budget, except for the additional 15 or 25 mil that Senator Mikulski threw at it, and took credit for saving the mission.
It is literally an ocean of knowledge you have and very intricate details of the project. My only question is, how significant do you think was your decision to cut basically more budget being poured into the project? I think this, from what you're saying, I think this speeded up the process, putting the HST up there. in the reservicing mission, which was very successful. What do you think?
I'm sorry, I'm trying to understand the
Yes,
question.
yes. So basically, you said initially that for the Hubble telescope, that you said, well, we're not going to be taking any more budget than the one that is allocated to us. That's it.
Right.
Do you believe this speeded up the process of the successful resurfacing mission?
No, frankly, I had a reputation of delivering at that time, delivering things on time and within the cost I predicted. So I had a decision process that looked at every new requirement that popped up. And typically one of the things that drives costs up is new requirements come up that weren't planned on or budgeted for, and they look terrific. And engineers, given their way, I mean, I face that today with some of the companies I consult for, given their way, we're gonna do that too. And oh yeah, it's no extra cost. They don't realize all of the secondary costs and, and so we didn't allow that to happen. I had my senior management in at 7:30 in the morning on Monday and Thursday. And we discussed, we worked very close as a team. We had loggerheads at times. There were times the engineers wanted to do something and the scientists didn't, and I was in the middle how to make them decisions. Turns out there were some of those that I made some decisions as scientists beat me up for, and it turned out if we hadn't made them, it would have been a real disaster. So I could give you an example, I'll put that in it if you want, but so I would say we did have a discipline. Every time the Cepelina and the hardware development people said it came into me for more money, I would go sit with them and try to figure out what we didn't need to do. And they got used to that. And so they got some discipline themselves, number one. And number two, I did have some money squirreled away that was in the budget. And I would gingerly let it out to solve problems when I knew if we didn't do that, it was going to end up either costing us more or building a risk in that we couldn't afford to take. And so we had a lot of autonomy, a lot less people telling us how to do that kind of thing. They left it up to me, mainly because they knew if I went to them, I'd want more. If I went to headquarters, get bringing in, they'd want more money. So they kind of let me alone, and they held our feet to the fire to perform what we had, and we did everything we can and did it. We didn't really. Later on Space Station, I had a different experience where we robbed from Peter to pay Paul continuously, but different worlds.
What would you say is your motto as a leader after all those years? Which were your principles as a leader when making decisions?
What are my principles when making decisions? First, the very first thing is I want to understand the implications of the decision. And that tells me number one, when does it need to be made? If you make a decision too early, it's got a way you don't have enough data probably. You'll never have enough, all the data, but don't make a decision too early. On the other hand, if I make a decision and if I made the wrong decision and it's recoverable or it isn't fatal, I will make a decision early to get everybody working towards a goal, because waiting will just learn it won't work later. I'd like to learn as early as I can if we've made the wrong decision. But if it's fatal, if I make a decision too early and I could have gotten a little more data, or if the decision to be made, if I make the wrong one, it's fatal, or will drive the cost up or something, but it's a very, critical decision. I will wait until I get the last minute, mainly because, at that point, I have to make a decision, but I think I have the most data.
You want to extinguish basically all your
decisions that have
alternatives to make,
low risks in making the wrong. If I make the wrong decision, I'll make them earlier. Ones that if I make the wrong decision and it's a potential high risk problem, or it creates a high risk or is a problem, if I make the wrong decision, I will gather as much data as I can and delay that as long as possible.
For a young
No
engineer
matter
like
how hard
me,
my team pushes
it's
me, no matter how hard my team pushes me, I will try to make them partner. The other thing is I always try to make the stakeholders partners in my decisions. I can't always do that. You can't make everybody happy, but I have found that if you make them partners, although they may not be happy, they'll understand why I made the decision I did. The same people will come back and beat the heck out of me if it doesn't work, but but I do try to make, that is, I try to make all the stakeholders partners. On Hubble, there's a couple things I did. I instituted something called the top 10. And the top 10 were the top 10 problems I had in front of me. And from my perspective, I made those every Monday morning. I sat down, I said 7:30, went over them, and those are the top 10 problems. What is the problem? What's the implication? What is the problem going to result in if we don't solve it? What is the status today about, if we're doing analysis, if we're going to test, if we've got somebody and what's the next action? And who's got it? It was a very simple, I try to fit it on one sheet of paper. Got to be two after a while, but it was never 10. And then I sent that out to every stakeholder. It went to Congress, it went to anybody who wanted to get on the list, get on the list. What happens if we reconnect them? And they can't reconnect, we've lost Hubble. So that was a big decision. It was a trade-off, whether we deal with the potential risk post-launch of losing the gyro, which there was a probability of doing that, okay, or not. And so I had every imaginable test on the ground, validated the zero gyro mode software. And then I got everybody, the science community, the contractor community, my team, the GAO, the Inspector General's office. We invited congressional staffers and had a meeting and went through everything we did, what the risks were, what the pros and cons were, and what our recommendation was. And my recommendation was we test the zero gyro mode. I had confidence in what we did to get there. I also had confidence that it would take several failures in order to not be able to reconnect the gyros after we did this test. And so even the GAO stood up and said, yay, verily, we're in. I made everybody in that room, if anybody thinks we shouldn't do this, I want to hear about it and we need to talk about it. Anybody. And we got a yay from everybody, but that was unheard of to get the GAO and Congress to take, but it was such a high visibility mission to the agency. We couldn't afford another disaster. Congress had a stake in it. GAO had the oversight. The Inspector General had the oversight responsibility, and plus we had, independent review teams. We brought in the chairs of those review teams into that. I mean, it was a big deal. So
it sounds like the pinnacle of your career.
I made it all partner. I made them all partners in the decision, and that's part of my philosophy was, make them a partner, no matter who it is. Make them a partner. Make them feel like they're part of the project and they really have a vote. And if they have a problem, listen to them.
I want to ask about the Hubble. Where was redundancy sitting in your priority list? Was that the top?
You mean in terms of fixing the Hubble?
Exactly.
What was the priority? Okay, well, we started out, and the engineering team, of course, we had to take the gyros, the solar arrays to replace, to take out the jitter. We had to correct, at least one, the optics, demonstrate we had corrected optics, although there was a lot of ground processing was done to get pretty close to the original specs, even without correction. But it was the minute we said that, people wouldn't have believed us. So we really just, kept doing that in the background. That's why I got such good imagery from Hubble before the repair mission. But backing up, so we had all these things to do. And so our engineering team, we can do them all. And General Pearson, who was the head of space flight then, was a Marine general who came back from the Desert Storm. And he called me and Randy Brinkley, who was the overall mission manager at our headquarters, he down to his office, and he said, "I'd like you guys to tell me what your priorities are." The same question you asked. So I said, well, these are the order we're going to do things in, but they're not necessarily the priority. We got to do this, this, and this, and these become secondary, but this is the order we have to do them in. And the engineering team, and he said, well, what's your measure of success? And I, like a dumb engineer, I said, we do everything we set out to do. And he says, no, he says, the measure of success is if the shuttle flies by and they blow the jets on the shuttle and come back down, they claim they dusted off the mirror. You crank up that software on the ground and tell them it was a little dust on the mirror, and you keep on going. And I said, I work with a pretty bright bunch of engineers, but even a brighter scientific community. Nobody's gonna, I don't think the lowest level reporters have, and he said, son, he said, let me tell you something. He said, I just come back from war. We defeated the Iraqis. So then Hussein went home. He convinced his people they won the war. He said, so your challenge is not even that difficult. and so that was it, the end of the meeting. He didn't say anything more like that than that. So what he really was getting me to do, without telling me, or what I immediately went back, I did exactly what he said. I said, what's our priorities? So I said a couple of things. I said, number one, I sat with my team and we said, we've got to at least replace one of the gyros. If we replace one of the gyros, and maybe it was even one piece of electronics, then we have gyros that'll get the reliability prediction will get us at least 3 to 4 more years till our next service ignition. So that's it. Number two, we have to demonstrate we've corrected the optics. So either CoStar, which corrects the imagery of the three radial instruments, or the wide field camera with the new corrected optics built into it, the replacement. One of those two have to be. After that, we should claim success. Everything else. So I went back to my team and said, tell me a flaw in that. And they blew up. We can do everything. We can do everything. And there was some pretty mundane stuff. And I said, okay. So I said, if we can't put the new dust cover on the magnetometer, I think it was, or something, and it doesn't go on, we're going to have to tell the press we weren't successful because we didn't do all 8 things on our list.
That persuaded them?
Wait, that doesn't matter. It's not important. I said, well, you don't tell them that after the fact. They're not going to believe you. I said, you got to tell them before the fact what your priorities are. So my priorities and the priorities I advertised were the gyros and the optics. The solar array wasn't important because that lost a couple of minutes of observing time, and we developed some software that damped out the disturbances very early in the light period. Compared to the 10 to 15 minutes when we started, we were down to 2 or 3 minutes of losing 2 or 3 minutes per orbit of disturbance until the solar arrays settled down. That was the jitter problem. Why we replaced the solar arrays was the design of the mechanism that deployed them. It bound up in the cold and released as soon as it warmed up, and that release was a twang, we called it, and the twang caused the solar rays to oscillate. And of course, when you're trying to point a telescope to a 10 millisecond stability, that doesn't work. You have to wait till that twang, and we developed some software that compensated for it and started the control system operating and countering the force. So, but anyway, so my only point is we need to replace the solar rays, but if we didn't, we were okay. We're losing 2 or 3 minutes in orbit, period. That was not a big deal. So that's what you were asking. The priorities were really these 2 things. we got those, and so then I began marketing that with the press and everybody, and they of course kept looking at it. But I basically went into it and why that was important. We demonstrated we repaired the optics. We're doing level 1 science with the observatory as we advertised before launch, the original launch. We effectively got the system such that it'll be reliably operating to the second servicing mission. We're building the new instruments that's continuing on the ground, and that's success. After that, everything else will, improve the performance and extend the life. And so that's how we sort of set the
So,
priority.
and in 2000, I consider this, from everything you said, basically the highlight of your career. Would you consider that as well?
The highlight of my career, did you
Yeah.
say?
Yes.
Well, it depends on how you measure highlight. I had a number of challenges. In space station, we had some challenges. I mean, one of the highlights of my career is to take the toughest Russian guy that you could ever imagine, old-line Russian guy, and sit with him in a bar for 3 hours and get him to agree to shut down Mir and support space station. I mean, that was not an easy task. But there were a lot of things I've done in my career. I could give you that are less visible than Hubble. See, one of the things that another philosophical thing, but it's important, is if you got your institution's number one problem, then they're going to let you fail. If the administrator picked you and put you in charge, he's going to make sure you got all the resources to be successful. And by the way, if you start talking and babbling like an idiot, he'll become a ventriloquist and talk for you. I mean, my point is they're going to do everything. An example, one of the things that is a no-no in the government is sole source contracting. Very difficult for me to select a vendor without running a competition. We very early in the mission made a decision to add CoStar, which we did at no additional money. And the only way we could do that in the schedule we were on and with the confidence we had that it could be pulled off is issue a sole source contract to Ball Aerospace for $50 million. And that's unheard of. A $1 million contract would take me a year to get through the system. Okay, if the only guy in the free world who made the widget, and I wanted to buy the widget from him, I'd still have to run a competition. Congress would make me run it, industry would make me run, and certainly the procurement integrity, chief procurement officer at NASA or Goddard Space Program. So management, I go into management council and I say, we're going to add CoStar and they didn't really understand Hubble, like this $50 million program. And I said, it's critical because it's going to correct the optics. And I went into what this wonderful thing did. And then I said, second thing is, in order to do it, I want to issue a $50 million sole source contract to Ball. They've got the box already built. They just need to put the optics inside the electronics. We know they know Hubble better than we do, and that part of Hubble, the instruments, and so we need to do it. There is no one else going to do it in time. I'm going to make the schedule. The science community wants this badly. They're supporting us. They haven't come down on NASA. The science community stood with us through this. Instead of they didn't join the pundits, they stood with us. And I said, we need it. The chief procurement officer said to me, where's the paperwork?
Of course.
I said, on my desk. He said, do you have a watch on? I said, yes. He said, give me your watch. Okay. And I'm senior management. I'm just a project manager or associate director. And he said, okay, got my watch. And so he said, you'll get your watch back when you give me the paperwork. And I said, I need to know what time to go home tonight. Was my answer to that, which one I want the watch back before I leave. They'll have to put the paperwork on his desk. That contract was out that Friday. Instead of being an obstacle, he took the lead and made it happen. I mean, that's the kind of support you get when you have the top priority. The people that normally tell you, it's on my desk, I'll look at it when I get a chance, pick it up and say, if I don't look at it, the boss is gonna know why I'm holding it up, or I'm gonna know. One time, there was a problem at Ball, and I wanted to proceed with something without the proper engineering review. I wanted to take a risk and proceed with it. And the engineering director, and they went up, and next thing you know, it's a Friday afternoon, I'm sitting in the Senate director's office. And he basically listened and said, I can't let you do that. I said, okay, he said, but I'm gonna, again, I told you I'm a stickler for schedule. I said, okay, it's Friday afternoon, 8 o'clock tomorrow morning, we're all gonna be in Boulder, Colorado, looking at the, this problem and get it reviewed, because Monday morning I wanna have it, the team install this. These are light baffles. We do a stray light test, and then when the stray light test is finished, you put in light baffles wherever there's possible, shining a stray light inside, and it's a standard process. So they did the test, they found the part, they wanted to put them in, and the engineering team wanted to go through the normal process with convene a review, we look at it, we analyze, write a report, and a month later, we'll tell you can install it, or a week later. And so I did that, of course. The part I tell you that is funny about it is this thing was coated with black paint. And the guy who painted, that was one of the questions, how well is it painted? How do we know that paint is here is gonna work? Then the guy stood up, I never forget his name, but I know where it is. He stood up and said, I've been doing this for 20 years or 30 years. And, I know what I'm foremost in my field, and So he passed it, and I said, here, look at it. He passed it, and I said, got to me, and I bent it a little bit, just flexed it a little bit, paint
It flaked off. Oh my God.
I bought dinner for the engineers, okay, the head of engineering and the head of quality QC at Goddard, when they came out, I bought dinner for them that night.
Was it thermal resistance paint?
Huh?
Was it thermal resistance paint?
Said it again.
Was it thermal resistance paint that they had on the surface, the one that flaked off?
Thermal resistance, you said?
Yes, paint.
Oh, it's black velvet. The paint is designed to maximum absorption. So it's
Okay.
like a fuzzy paint, and its goal is to absorb the incoming light, scatter it, and not reflect it back. Okay, and so
Okay.
the baffle is nothing more than like a lollipop, but it's flat, just a flat round or square or whatever rectangle on a stick. That basically, it's tied to nearest structural member. And it's supposed to have enough stiffness that it it doesn't vibrate loose, and so we don't want the paint to flake. Well, this thing, the paint would have flaked, and we would have had, an interesting, would have not been good. We would have had a different problem.
Engineering problems like the ones you're describing are what fascinates me about aerospace in general, even though it is a little bit different when we're talking about fighter jets, because those are the ones that I'm working on. The nature of the problem is very, very similar. It is very similar. Of course, yours is way more high stake than what I am dealing with, but the nature is the same.
It doesn't matter how big, you have a lot of these same problems at home, right? Air conditioning, plumbing problem, they're different.
Yeah.
I mean, the implications are different, but they're the same kind of problems. You decide you're going to take a shortcut, and there's something that you didn't expect, or you go buy a part and you find out that you didn't put the A on the part number, and you got the different part, or I mean, the different problems. I mean, since right out of the get-go out of Grumman, I became a problem solver, not by design, but it just, everything I got thrust into seemed to have a problem. And then later on, when there was a problem, it was me they went and found and said, hey, we need you to do this, we need you to do that, because a reputation of being able to solve problems, or being able to build a team that solved the problem, not me. You know, in most cases, I could characterize the problem and get the right people, but they generally had the expertise to solve the problem.
So you would say you were basically, would you say the most important thing within a team is a master facilitator? Somebody who can put the right people exactly where they should be to solve the problem as efficiently as possible.
And keep them motivated, keep them working together, motivated, keep them communicating, and jump on it faster than a technical problem, jump on a personnel problem. I mean, don't let that lie. Don't be afraid to jump in and do whatever is needed. And usually it's a negotiation, you know, and you try to bring people together and find out, you know, what the differences are and where the common ground is. And in some cases, it's a matter of risk. In some cases, you just have to make a decision. And others, you say, okay, we're going to try it that way, and we'll get to this point. We'll know whether it's successful, and we'll try it your way. Or we in one case, we went and we had an argument on what set of mirror. We needed 3 sets of mirrors for the coastal. Which ones we build first? We had a big argument. You know, the optical people had one view. The engineering, the management engineering leadership on the surfacing side had another view. We ended up doing the 3 in parallel. We put enough money, and it turned out that was the smartest thing we ever did. The 2 of the people who we would have expected to knock it cold, or for all I know, they're still trying to make these little mirrors. And one guy who we decided to give a guy who made mirrors for projection TVs, but nearly made space mirrors, but he made aspherical mirrors, which was important, off-axis mirrors. Tinsley gave it to them. The other 2 guys one got $1 million, the other got $1.5 million to develop the first of one of the 3 mirrors. This guy got $800K. He came in at $800K. He built the first mirror, sent it to us. Our optics guys checked it out and said it was perfect. It was one of the best mirrors they ever had. He did it in 3 months. These guys still hadn't figured out how to do it. He comes back and says, I think you're going to need a set of spares. And I can fit a set of spares in that budget. And he delivered a set of spares. Oh, by the way, he delivered not only his, but he delivered the other 2 mirrors within that budget. The other 2, give me the you know, the prescriptions for the other 2. I'll do all 3. And by the way, I can give you a set of spares. He did that all for $800K. As far as I know, the other 2 guys are still working on it because they didn't deliver. They couldn't deliver. And they were two of the top optics houses in the country, except they weren't geared to build a mirror the size of a quarter that was aspherical. And they try to apply big processes to little. You know, you needed a different analytical technique, a different polishing technique, and they try to scale down what they were doing. I mean, you know, that's the new space. I mean, that's what it's all about. The guys who try to scale down and say, I'm going to bust this big using the same processes I used to build a $700 million communication satellite, or a scientific satellite. They're not going to get there. You really do have to do what these young people out of Stanford did that formed Skyboxes. You had to throw out a piece of paper and say, okay, what do I need? And start building up, decide what your optimization around, and optimization in that case was around cost, and resolution and reliability. I mean, those were the 3 parameters.
Yeah.
Thank you for watching this educational interview with Mr. Rothenberg. I hope you enjoyed it. Most of all, I hope you learned from it, and I will see you in the next one.